Okay, now same chapter, current electricity, and the topic is Ohm's law. So according to Ohm's law, voltage is directly proportional to electric current provided resistance / temperature of the conductor is constant. I repeat, voltage is directly proportional to electric current provided resistance temperature of the conductor is constant. Mean voltage directly proportional to electric current. V is equal to constant resistance times R, which can be written as V is equal to IR. Now, the resistance R can be written as V over I. V is the voltage, which is measured in volt, current in ampere, and volt per ampere is called ohm. So the resistance is measured in ohm. Now the definition of the resistance: ratio between voltage and electric current in the conductor, in the wire, is called its resistance. So it's a ratio. The ratio between voltage and current in a conductor is called resistance. Now, resistance of wire, of conductor, will be 1 ohm if 1 volt potential moves 1 ampere current in it. So resistance of the wire will be 1 ohm if 1 volt potential, 1 volt voltage, 1 volt EMF drives 1 ampere current in it. Now, graphs. Voltage at the y-axis, then current at the x-axis, current in ampere, voltage. So it's a straight line passing through the region. And the gradient of this graph is equal to resistance. This is the graph number 1. Voltage at the y-axis, current at the x-axis. Similarly, if the graph is current at the y-axis and voltage at the x-axis, again straight line passing through the region, but the gradient is the reciprocal of the resistance, mean 1 over resistance. And then when voltage at the x-axis or current at the x-axis and the resistance is plotted at the y-axis, for the Ohm's law, resistance is constant. So this is straight horizontal line because the resistance for the Ohm's law is constant. Similarly, if the voltage is plotted at the y-axis or current at the y-axis and the resistance are at the x-axis, then it will be constant vertical line because the resistance is constant. Okay, now suppose the table among voltage, current, and resistance. Voltage in volt, current in ampere, and the resistance in ohm. Now suppose the voltage is 20 volt, then 40 volt, then 60 volt, and suppose the current is 2 ampere first, double current, double voltage, 4 and 6. So the resistance, which is equal to V over I, 20 divided by 2, it's 10. 40 divided by 4, it's 10. 60 divided by 6, it's 10. Look, the voltage is increasing, current is increasing, but the resistance is constant, mean the resistance of any resistor is independent of its voltage and current. If the voltage is increasing, no effect on the resistance. If the current is increasing, no effect on the resistance, because V and I both are directly proportional. When voltage becomes double, current becomes double, so the ratio remains same. So the voltage and current has no effect on the resistance. Now, factors affecting the resistance. Number one is, the major factor is the temperature. So, first, metals. When the temperature of the metal increases, resistance increases. Look, temperature in degrees Celsius at the x-axis, resistance in ohm at the y-axis. So the resistance is increasing. So gradient is almost constant, not perfectly constant, okay? So when temperature of the metal increases, resistance increases. It means if the temperature is constant, then the graph is a straight line. So it is called the ohmic conductor. So the ohmic conductor only when resistance constant, temperature constant, no increase in temperature. But practically, when current flows the wire through the metal, there is some heat dissipated. According to the formula, energy is equal to I square RT. Temperature increases, resistance increases, hence the resistance of the metal increases. So basically, metal is a non-ohmic conductor because it cannot maintain its resistance. Thus, the metals are assumed to be ohmic conductor, but practically they are not ohmic conductor because in reality, their resistance cannot be maintained when current is supplied to them. So if it is assumed that the temperature of metal is constant, this is just the assumption. If this is the assumption, then the resistance of the metal depends on its length, directly proportional to length. Number two, resistance inversely proportional to cross-sectional area, which leads to resistance inversely proportional to diameter square, or resistance inversely proportional to radius square. So resistance is directly proportional to length, inversely proportional to area, only if temperature is constant. Now, R is equal to constant resistivity L over A, but when the temperature is constant, and this rho is called resistivity, and it is written as RA over L. Now, resistivity is the resistance of a conductor having unit length, mean 1 meter long, and unit square cross-sectional area, mean cross-sectional area 1 meter square. So resistivity is the resistance of the conductor having unit length and unit square cross-sectional area, mean when the wire has length 1 meter and cross-sectional area 1 meter square, then its resistance is known as resistivity. So the resistivity rho is equal to RA over L, mean R, area 1, length 1. That's why resistivity and R equal when length 1, area 1 unit square. Now, resistance is measured in ohm, area in meter square, length in meter, cancels. So the unit for the resistivity, ohm meter. Don't write meter ohm because it is represented as milliohm. It is known as milliohm. So ohm meter. This is the unit for the resistivity. Now, the reciprocal of resistivity is called conductivity, and it is represented by sigma. So sigma is equal to 1 over rho, and the unit will be ohm meter whole power 1 minus 1. So ohm minus 1, meter minus 1, but 1 over ohm power minus 1 is represented by S, and S means Siemens. So S times meter power 1, this is the unit of conductivity. Okay, if the graph is plotted, current at the y-axis, voltage at the x-axis, when the wire is assumed ohmic conductor, mean when the temperature is constant, then it's a straight line passing through the region. But practically, when current passes through the wire, it heats up according to formula I square RT. So its resistance increases. So the graph will be like this, mean the gradient is decreasing because the gradient is equal to 1 over resistance. When the gradient is decreasing, mean the resistance is increasing. So these two graphs are reciprocal to each other. Here the voltage at the y-axis, and here the resist and the current at the y-axis. Okay, now the number 2, suppose instead of the wire we have some semiconductors, which are oxides of elements of periodic group, fourth periodic group, elements of the fourth group of the chemistry periodic table. So they are the semiconductors, for example, diode, thermistor, LED, LDR transistor, etc. So in these semiconductors, when the temperature increases, resistance decreases, totally opposite to the metal. Suppose the temperature at the x-axis, resistance at the y-axis. So this resistance is gradually decreasing. At constant temperature, voltage and current graph will be straight line, but practically when the when the current is supplied to the semiconductor, its resistance decreases, so the gradient of the graph will decrease. So semiconductor is also the non-ohmic conductor. Similarly, when voltage at the x-axis, current at the y-axis, so actually this is the graph for the ohmic property, but practically resistance decreases. Hence, the gradient of this graph increases for the semiconductor. So these two graphs are for the semiconductors. Now, when current passes through the resistor, some energy is dissipated. According to the formula, potential is equal to work done per unit charge. So the voltage across the resistor means the energy delivered across the resistor per unit charge. So we can write the electric energy dissipated is charge multiplied by voltage. So energy is equal to charge multiplied by voltage. Now, the power is the work done per unit time. So energy divided by time mean the power is equal to charge multiplied by voltage divided by time. But the Q divided by T is equal to I. So the power is equal to IV. So this is energy, this is power. Now energy is also equal to power multiplied by time. So energy is equal to IVT. This is another formula for the energy. Now if the conductor is ohmic conductor, mean it is obeying Ohm's law, then we can write V is equal to IR, or I is equal to V over R. So in this formula, power is equal to I and V is replaced with IR. So power is equal to I square R. And energy is equal to I square RT. Number 2, power is equal to IV when the I is replaced by V by R from the Ohm's law. Then the power will be V square over R and the energy will be V square over R times T. So these are the relation for power and energy.